Okay, so now that we're recording, about the reading quizzes, um, a chunk of you have a class immediately before this one, and I can't really imagine anything worse than an 8 o'clock a.m. remote class. I mean, an 8 o'clock a.m. in-person class is bad enough, but um, yeah. But anyway, so what I'm going to do is just open the reading quizzes and have you do them at your leisure, to try and keep you guys actually reading the material before you start the quiz. There will be a half-hour time limit, but it should not take anywhere near that. So the quizzes will be open for a good chunk of time, and this one I think is open till noon now, so that I don't want people stressing out about deadlines. That's counterproductive to the whole purpose of everything. So let's get going. We'll kind of catch back up. So last week we started a review on thermodynamics, catching back up with what you learned from Professor Akbar, and I want to go back and do a couple of the quick examples that are in here, and then go on to entropy. So there are two quick problems that we want to look at, and first has to do with this notion of mechanical work, and this is just really trivial. This is physics 1 type stuff, but we want to look at a no, there we go. Okay, so the problem at hand here is calculate the work done by a mole of an ideal gas when it's isothermally compressed from 100 cubic meters to 10 cubic meters at a constant temperature. Okay, so if we're compressing an ideal gas isothermally, what's that going to tell us about the process? Right? Why am I picking such a trivial example?
Ideal gases are relatively easy in calculating.
Yeah, so it is relatively dang it. I forgot to do the top hat quiz. Okay, so everyone gets free attendance this morning. So everyone is present. If you're not here, let me know and I'll mark you as absent. Okay, so yes, ideal gases are relatively easy, right? But I think the point that I really want to make here is we're doing it isothermally. So if we're compressing a gas isothermally, are we doing it slowly or quickly or? Right, we're obviously doing it very slowly, right? Because from the ideal gas equation, what happens if you reduce the volume of a gas by if you rapidly were to compress a ideal gas, right, you're going to get a temperature increase, right? So the fact that we're doing this isothermally means that we're essentially trading off volume for pressure in a 1-to-1 relationship, meaning that this is going to be a reversible process, right? Okay, so if we start out with, of course, we need the ideal gas equation, right? Right, pressure volume is nRT. Pivnert is still one of my favorite things to say. I don't know why. Okay, so what's our work equation look like? Right?
Work equals, for ideal gas, I think work is equal to just PV, I think, or delta P times delta V.
Yeah, right. So this is just pressure volume work, right? And so if we're compressing it over a distance, right, we need to integrate over what we're compressing, right? So is, right, so work is just going to be the integral of P dV, right? And since this is an ideal gas, right, we just substitute in nRT, the integral, we're compressing from 100 to 10, right, of dV by V, right? And this is everyone should know how to do this analytically, right? So this just becomes nRT, the natural log of V from 100 to 10, right? So this becomes pretty trivial. We have 1 mole, right? 8.3 joules per mole Kelvin, right? And I said it was 500 Kelvin, right? And if we do our natural logs, we get -1. So therefore, we're going to be approximately 9,500 joules, right? So a really, oh, that's not what I wanted to do. There we are. Straightforward, a really straightforward calculation, right? And it seems kind of trivial, but we'll think about this when we go back to when we're trying to motivate the notion of Gibbs free energy, right? And we're going to think about this a little bit on Wednesday when we develop the notion of a free energy from the fact that for a reversible process is an isentropic process, but that's not always the easiest thing to think about. And the direction of spontaneity is, of course, the one that lowers Gibbs free energy, but that's also the direction that gives us an entropy increase. And we can think about this compression of a gas or expansion of a gas again as a way of motivating the Gibbs free energy.
Where did the -1 come from? I'm sorry.
Right?
I see the 2.3, but where did the -1 come from?
Hold on. We are, what did I do here?
I think the log of 0.1 is -2.3, right?
Yeah. I just
flip the integral.
What's that? So we're evaluating this
Flip
from
the integral.
So it's 100 to 10. So I'm Yeah, so this is just the subtraction, right?
I forgot flipping the integral. I'm clear now.
Yeah. I'm just making sure I didn't. I like to think about these things because again, my ability to make simple mistakes is infinite. So I just want to make sure that I didn't screw something completely up with with a simple example, because it's worse things have been known to happen. Okay, so the second example is just thinking about formation, reactions in specific heats, right? So here I say we have a constant pressure specific heat of aluminum is given by this polynomial form. These polynomial equations here is typically the way that specific heats are fit and tabulated, right? It just happens that a lot of times they sort of have this form, right? And what about the specific heat lends itself well to this polynomial form? So if you can see the one for alumina, right? We have a constant term plus a linear term here, and then we have a it's not, I guess it's right, and then we have this 1 over t squared term with a very large number out front, right? What about the nature of the specific heat that sort of lends itself naturally to this type of form? Right? So the specific heat is a monotonic function of temperature, right? Meaning that the higher the temperature, the higher it is. And so having this gives you this 1 over a higher power of t gives you a nonlinear correction, but it also guarantees that as t goes up, this term goes to 0, so that you're never going to go, you're never going to have an inflection, you're never going to start to dip back down, right? So it's just a mathematical convenience. Okay, so here we have the specific heat of alumina and the specific heat of aluminum, right, over some temperature range, in this case 298 Kelvin to 932. And I also give you the heat of formation of alumina at room temperature. And we want to calculate the enthalpy, Montaigne. Oh, that, I'm not sure where that word came from. All right, that shouldn't be there at all. The enthalpy of, oh, that should be change. How did that change to Montaigne? Autocorrect is really weird sometimes. Of aluminum and alumina. Okay, so okay, so if we want the enthalpy change of aluminum, right? We know that we're going to have to do the enthalpy of aluminum at 900 minus the enthalpy right? Okay, so what's the enthalpy of aluminum at 298 by definition? Right, this is 0, right? But all the enthalpy of pure elements, right, at 298 is by definition 0, right? So this just is going to become, we just need to calculate the enthalpy of aluminum at 900, right, which is just going to be the specific heat. 0, 1, 2, 4 T dt, right? And that's equal to, right, we get 16.93 kilojoules per mole, right? Now for alumina, right? So at 298, the heat content of alumina is the enthalpy of its formation, right? All right, so H Al2O3 at 298 is equal to, right? And so now we need to calculate the heat. This is also kilojoules per mole. So now we need to compute the enthalpy change, right? So we're going to have the integral, again, from 298 to 900, right, of 106.6 plus 0.0178 T minus 2,800, right, 2 million. Right, and this works out to be 70.61 kilojoules per mole, right? So therefore, that's the change. So the total enthalpy of alumina at 900 right? Right, no magic there, just sort of a refresher on manipulating.
It's not really important, but you forgot the T next to the second term in the alumina interval.
Oh yes, you're right, thank you. Yeah, it was there, I just not legible. All right, so, okay. Let's, oh, I need to share this back, okay. Okay, I'm back on the, sorry, I'm working on like 2 different machines so that I can have things set up weird, and switching back and forth is not always convenient. Okay, so enthalpy in the second law. I gave my long rambling story about a car going downhill. We looked at the picture of sexy, sexy Boltzmann. And we come back to start with shoot, types of entropy. Okay, so most of the time when we think of thermodynamic entropy, right, we're really talking about or thinking about configurational, right? We think about expansion of gases and things like that. But we also really need to consider thermal entropy, right? The number of different possibles of particles can arrange themselves over energy levels, right? The entropy attributed to electronic probabilistic occupation of states, the quantum or electronic entropy. And then we have entropy associated with randomization of magnetic and dielectric moments, right? And these are all really important for phase transformations, right? Why is mercury a liquid? Right? It has to do with the quantum mechanical aspects, and a lot of that actually has to do with the electronic entropy of the system, right? So weird things can sort of happen, right? We also have lots of phase transformations that make science and nature papers that relate to things like magnetic moments or dielectric moments. And we'll talk a little bit about some of these later on in this semester, right? So when we think about things like spin glasses and other exotic states of matter, some of those states of matter have to do with quantum or electronic entropy, others have to do with magnetic and other types. So this is actually very much related to the phase transformation problem. But let's start with configurational, right? This is what we're most familiar with. This is the enthalpy associated with atomic disorder, right? So the illustrated example of this is the entropy associated with the formation of vacancies in a crystal, right? Okay, so if we have a crystal lattice, right, and we want to put n vacant sites and n atoms on a total of little n plus big N lattice sites, right? The number of ways of distributing that is going to be little n plus the total number of lattice sites factorial divided by the number of vacancies factorial and the number of atoms factorial, right? Factorials get really big really fast, right? So luckily we have Stirling's approximation, right? Okay, so what's the deal with this? Why does anyone know why this works?
Because of the definition of the exclamation. So when you take natural log of that, it basically creates a form where the equation is comparable.
Yeah, right? Right, so it's one of these, if you start with the, 1 there's a really easy derivation if you start from the definition of the gamma function, right? Which you may or may not remember. But anyway, I can just throw this up here real fast, right? So if we look at, right, we can show that the factorial has to be equal to this using the gamma function, right? And then it's simply a matter of doing a little exponential and logarithmic algebra, right? And you can see where things can fall into place, right? There's other ways of deriving it. It's interesting to note that, you know, Stirling's approximation really only works well with large numbers, right? It's asymptotically correct, so it's really bad for things that small x. But once you're above, say, 10 or so, then it starts to work really well. Okay, so if we plug in Stirling's approximation into our configurational arrangement here, and we plug in and do a little simplifying, we see an expression that looks like this, right? So we've got our both, right? This is our natural log of our configurations, Boltzmann's constant. And what's important here is that when we do the theory of mixtures, if we think about an ideal mixture, we end up with a relationship that looks awfully the same, where this is the mole fraction of A, this is the mole fraction of B. And if we think about this as being the fraction of atoms and the fraction of vacancies, we end up with a parallel construction, right? So we're going to see things that take the same mathematical form again, and it all has to do with the configurational entropy. Okay. So this first part, we don't even need to draw out, right? If we calculate the total number of configurations for 8 atoms and 1 vacancy by drawing the configuration, right? We've got 9 lattice sites, 1 vacancy, right? So we just essentially, we have 9 different configurations, right? With the vacancy on each one of the possible sites, right? This second one, calculate the entropy change due to introducing 10 to the 18 vacancies in a mole of perfect crystal, right? That's just really simply just plugging right back into this equation here, right? So the most important part, though, right? It's just plug and chug. The question is, does the entropy increase or decrease? Right? Obviously, the entropy is going to increase, right? Because there's only one way to arrange the configuration of a perfect crystal, right? But we have lots of different ways of arranging 10 to the 18 vacancies on 10 to the 23rd lattice sites, right? And in this case, the entropy increase is 2 times 10 to the minus 4 joules per Kelvin, right? So if you plug that in and give it a try, you'll see that that's where it comes out. Why would I pick this example of vacancies on the crystal lattice? How is this example relevant to what we're going to do later? Right? A big topic is diffusion for this course, right? What is the primary mechanism for diffusion in a solid? Right? Vacancies, right? I have a solute that hops into, hops from vacancy to vacancy, essentially, unless it's interstitial, but that's different. You can imagine how difficult diffusion would be in a perfect crystal, right? Then I need two atoms to switch places, right? That's got to have a huge energy cost associated with it, right? Two atoms jumping out of their lattice positions to switch. Whereas if I have vacancies in my crystal, all I have to do is have a atom jump from an occupied lattice site into an empty lattice site, right? The other thing is, what we see here is that because there's a entropy increase associated with the formation of a vacancy, that if the enthalpy is small enough, right, the Gibbs free energy mean calculation essentially tells us that there's going to be an equilibrium concentration of vacancies in a crystal, right? So we're always going to have vacancies around. And this is really important for phase transformations in alloys such as aluminum, where you have precipitation and growth of secondary phases. At high temperatures, we have a lot of vacancies in our crystal. If I quench them down, if I quench quickly enough, I lock in those vacancies. There's not time for them to be removed, right? So I'll end up getting a faster phase transformation in that state in a rapidly quenched material than if I were to cool it slowly, right? And in fact, I get precipitate free zones around grain boundaries, right, in these alloys as well, because grain boundaries act as sources and sinks of vacancies. So the vacancies have a chance to be annihilated and approach their thermodynamically desirable configuration near those grain boundaries, but not in the center of a grain, right? And so vacancies, the content of vacancies and the stability of vacancies are actually really important for later on concepts in this class, right? And if you didn't catch any of that, don't worry about it. We're going to talk about all of these things in detail sort of later. Another really critical type of entropy for this class is the thermal or vibrational entropy. Right, as the atoms or ions in a solid vibrate, the exact value of their energy constitutes the thermal entropy, right? So to really understand this on any kind of level, we need to really appreciate that the vibrational energy levels of atoms in a crystal are quantized, right? So this touches back to the the biggest problem in classical physics, which was, of course, you know, the black body radiation problem, right? And so without an understanding that we have quantum energy levels, quantized energy levels, we end up with crazy issues like ovens. If you try to theoretically calculate the energy output of an oven, you end up with an infinite energy. And this concept of thermal entropy, the way we have to think about things being quantized, falls back into that same problem, right? So this relates to the last sort of standing problem in classical physics that led to the development, or one of the problems that led to the development of quantum physics. So if we assume we can take a simple model of a solid, and if we just assume that the atoms or the ions are little weights and they're all connected by miniature springs, and we have this model of a simple harmonic oscillator. And we're not going to go through the physics, but it isn't too hard to show that energy will be quantized with the spacing between the energy levels given by this equation, which you've probably all seen before. Right, H and U are Planck's constant and the characteristic vibrational frequency of the bond. This is essentially the model of a Einstein, the start of the model of an Einstein solid. Okay. So the characteristic vibrational frequency of the bond is going to be related to the bond stiffness, right? Just like the tighter you make the string on a musical instrument, the higher the note, the higher the frequency, right? So the stiffer we make our bonds, we're going to increase the vibrational frequency, right? So this here is our spring constant, right? And this you probably touched on when you looked at atomic bonding in MSE 2010. I'm going to skip over a huge amount of details because they're not particularly relevant for the point I want to make here. But if we put all of this together, essentially what we get is that the spacing of the energy levels for strongly bonded solids is greater than that for weakly bonded materials. And this is going to have really important physical ramifications that we'll hit on in the next couple slides, right? And this has an analogy in music, right? Each octave doubles the frequency, right? So that means it is essentially the same thing. The energy, the spacing becomes smaller and smaller, right? If we're doubling the frequency, the wavelength separating the notes, the difference in the wavelength becomes smaller and smaller and smaller as we go up in pitch. Okay, so I'm not going to really go into the details of lattice vibrations. You'll get that when you study quantum solids. Have fun calculating, the electron in a potential well. You'll do that ad infinitum. But I'm going to present something from this Einstein solid model without any proof or derivation, right? This is work from Einstein in, I want to say, what year? Um, 36 comes to mind. I'll have to look it up. But anyway, Einstein showed that the thermal entropy per mole, if we have a solid of Avogadro's number oscillators, and they all have a constant vibrational frequency of mu Einstein here, we end up with the thermal entropy formulation that's like this. If our temperature is high enough, we can use this approximation that for small x, e to the x is approximately x plus 1. This is another one of those useful approximations to try out, right? If you've never done it, just take 1.001, or just take e to the 1, and you'll see it's like 1.001, or 0.001. Yeah, e to the 0.001 is about 1.001. But if we substitute that in and do some evaluation, we get a much simpler form where the entropy is going to be this natural log of kT here with the 3 times the gas constant out front. What's interesting about this is that more complicated models for solids, like the Debye model, which assumes that we have a distribution of frequencies, gives virtually the same result at high temperatures. Why am I bothering to go through this? Okay, so there's some important physical things that we want to consider. So the thermal entropy here is a monotonically increasing function of temperature, right? As temperature increases, atoms can populate higher and higher vibrational energy levels, right? So the uncertainty in distributing these atoms among this larger number of accessible energy levels constitutes the entropy, right? So we have to, the key thing is we have to make sure these energy levels are accessible, right? And this is where the quantum mechanics aspect comes in, because classical physics basically says all of these energy levels are accessible because I can have fractional bits, right? But quantum mechanics says no, you got to make the jump in a quantized state from one energy level to the next, right? So we have this key concept. Okay, I promise I'm getting to a point here. So the thermal entropy is going to decrease with the increasing characteristic frequency, right? So if I increase this, our thermal entropy is going to go down, right? And so now here we have that this vibrational frequency scales with the bond strength, so that for a given temperature, a solid with weaker bonds are going to have a higher thermal entropy. Okay? So we have a fairly straightforward physical reasoning here that we can make, right? If the bonds is strong, the spacing between the energy levels is going to be large, and for a given change in temperature, only a few levels are accessible, right? So we have very little uncertainty with the vibrational mode, the distribution of vibrational modes that are present. So therefore, entropy is low. In a weakly bonded solid, though, we're going to have many more levels that are accessible. The entropy is high, right? So this is really important for phase transformation. How and why? Okay. Temperature-induced phase transformations tend to occur in the direction of increased thermal entropy. Okay? So transformations are going to occur from phases of high cohesive energy, bond strength, to those of low cohesive energy, right? The trivial one is melting, right? We have a solid bond, solid uh, material going to a liquid, right? Obviously, we're going from perhaps ionic, covalent, metallic to van der Waals type interactions. But even if we think of solid-solid phase transformations, we tend to have close packed structures at low temperatures that are going to transform to more open structures at higher temperatures, right? Which is interesting because we'll see lots of material that have high temperature phases that are BCC. The probably most well-known example is titanium, right? What's titanium at room temperature? Right, alpha titanium is hexagonal close packed. What happens when we increase the temperature? Right, we go to BCC. Right, so we tend to go to slightly more open structures at high temperatures. It's a weird thing also happens is that a lot of materials happen to have BCC phases at high pressures, which seems counterintuitive, right? It turns out that that's actually a quantum mechanical thing for electronic structure. So we can't always say that, we can't always use the nature of the structure to determine which way things are going to go. Sometimes we get counterintuitive things that happen. But in general, the direction of our temperature-induced phase transformation is going to follow this notion of increased thermal entropy. So we're going to go from close-packed, stiff structures at room temperature to higher more open structures at higher temperatures, meaning, important for properties, the elastic modulus of the high temperature phases, tend to be lower, right? They're not as elastically stiff as the room temperature phases. Okay, and so if we have a phase transformation, and due to that, the vibrational frequency changes because we're changing the nature of the bonding. We can calculate the change in thermal entropy due to the transformation directly from the frequencies, right? So if nu is greater than u prime, right? So this follows our expectation that if the vibrational frequency of our original or low temperature phase is higher than that for our high temperature phase, we're going to have a positive change in entropy. Okay. So on Wednesday, we're going to get into Gibbs free energy. We're going to talk about chemical potential and activity and how this relates to the thermodynamics of mixtures and binary phase diagrams, right? So this is essentially the plan for the rest of the week. This should all still be review, but then on Monday, a week from, well, that's Labor Day, right?
Yes.
Do we even have Labor Day off this semester?
I don't know. I'm just thinking that.
I think we do.
We
Classes
do.
don't show up on our schedule.
Okay, so
Yeah.
so we'll be taking this stuff to solidification the following Wednesday then. So a week from Wednesday, we'll be talking about how this all relates to solidification, which is the first phase transformation that we're going to talk about, going from solid to liquid and liquid to solid. When will the readings for each week be assigned? There won't be an additional reading assignment this week. There'll be another reading assignment that will be due in 2 weeks from today. Right? The first one was a little long, but the payoff is you get a week off when doing any reading for this class. Cool. Guys, I really am actually pretty pleased with how positive everyone is in the chat and that you're answering each other's questions. So keep that up. I am listening to everyone's songs. As you guys said that, there's a couple things I'm noticing. Is that the women in the class tend to be much more adventurous with their suggestions than the guys, which is which I don't know. I also noticed that our students of color and international students also tend to be much more diverse with their music choices. The white guys seem to really like Pink Floyd. Quite a lot. So, but it's not all the same song. It's just a general trend. There are, of course, lots of outliers. But anyway, I'll post the complete Spotify list up on Carmen in the next couple days. So the next set of notes will be up tomorrow. Make sure you download them before class Wednesday morning. And we'll finish up a couple minutes early. And take care, everybody, and we'll see you Wednesday morning.
When you say notes,
What was that about notes?
yeah, what do you mean by the notes? Like the
next set of slides will be available up on Carmen on Tuesday.
Okay, yeah, like so lecture slides. All right.
Lecture slides, yeah. So you have them in advance.
Real quick, does the reading have like specific pages or chapters listed anywhere?
So the first reading assignment was just chapter 1 in the textbook, the Porter and Easterling book.
Okay.
Right? And then there is no reading assigned for this coming week.
Okay. All right. Sounds good.
Okay. Any other questions before I disappear? Okay. Have a good one, everybody.